Hi everybody, very warm welcome to Vedantu JEE English channel, and like I always say, Andariki Namaskaram, Ellarku Swagatam, and a very warm Vanakam to Vedantu JEE English channel. This is me, your master teacher Nabamita Ma'am, and I am here to let you all know about the inorganic exceptions, and I think that we will be completing this chapter, like this session, in about like 1 hour or so, not more than that, definitely not more than that. I think that's it we will require, and within this time we will be able to complete the coordination compounds, exceptions. We will be able to complete periodic properties, p block, baki s block is swaha, om swaha. That happened to it, right? It's already poof, all gone. So now you have to read less, you have to study less, and I think that's a good thing for this year, isn't it? So don't get scared, and let's try. Let's see if we can complete this chapter as soon as possible. Okay. Alrighty, everybody. So inorganic chemistry, and of course we're going to start with, my favorite chapter, coordination compounds, guys. How can I let this go, right? How can I let this go? I have to complete this chapter. So in coordination compound, we do not have many exceptions. It's not so much, but just a little bit that we are going to talk about right now. So first of all, let us have a look at this place here. What do you see here? You see that if CO plus 3 is bonded with oxygen donor atom, that means that H2O and oxalato. Yes. So these are ligands, isn't it? You all know these are ligands. Yes. So the ligands, they have donor sites, right? The donor sites or the donor atoms are the ones that provide them with the electrons, and that's how they are connected with each other. One second, guys. Sorry, my legs were paining, so I was sort of standing on the chair. I had to remove it because otherwise I can't walk like this now. Anyway, so you know why I don't wear specs now? Do you see how the light reflects, and sometimes it feels like I do not have my eyes? Yeah, this is why I do not prefer wearing glasses. But today somehow my head is paining from looking at the screen and the light and everything, so I have to wear. Anyway, back to the studies, everybody. So as I was telling you, CO plus 3, that means cobalt when it is a trivalent atom, and when it is bonded with oxygen donor atom. For example, you have oxalato, that is C2O4, you have H2O. In case of H2O, the only donor site that you have here is oxygen. All right? Yes? Okay. Now, this ligand then at only specifically at that point of time, the ligand then starts acting as a strong field ligand. Are you understanding? Yes. Only with CO plus 3, only with cobalt plus 3 bonded atoms, these act like a strong field ligand. Otherwise, we do know that H2O, water, is a weak field ligand, don't we? We know that. Now for copper plus 2, if it is bonded with water, then the ligand act as a strong field ligand, only with copper. Otherwise, once again, my dear students, we do know that water is a weak field ligand. It's not a strong field ligand at all. In case you have a nickel in plus 4 oxidation state and it is bonded with fluoride ion, you all know that anionic ligands are the weakest and they fall in the spectrochemical series on one end, where these are where you can find all the weak ligands, isn't it? The anionic ligands are on the extreme left side. That means they are the weakest, they are not at all strong, and you find carbon monoxide to be the strongest ligand, isn't it, everybody? So we know that F minus, Br minus, I minus, Cl minus, these are all going to be weak field ligand. However, only when this F minus fluoride ion, when they are bonded with nickel in plus 4 oxidation state, they will act like a strong field ligand. Okay. So these are the only things that you have to remember. Cobalt plus 3, H2O, or oxalato, that means oxygen donor atom, are going to act like a strong field ligand. All right. Next, what did I say? I said that Cu plus 2, that means copper in plus 2 oxidation state, water is going to act like a strong field ligand. Ni in plus 4 oxidation state, fluoride ion is going to act like a strong field ligand. If it is Fe plus 2 and Mn plus 2 are bonded with NH3, then also the ligand act as a weak field ligand, which is true. NH3 is not very strong. It is in the moderate range. It falls in the middle somewhere, okay? So you see that it still acts like a weak filled ligand when it joins with Fe plus 2 and Mn plus 2, right? Apart from that, in the 3D series, elements in plus 2 oxidation state from outer orbital complexes up to NH3 in spectrochemical series. Okay, what do we mean? We mean that in 3D series, the elements which are in plus 2 oxidation state, they try to form outer orbital complexes. Outer orbital complexes, they have high spin complexes. Yes, in case of inner orbital complexes, what happens? Pairing happens, so they form low spin complexes. When they form outer orbital complexes, there is high spin. That means there is more space that is left for the electrons to cover, right? Okay, and they form outer orbital complexes up to NH3. That means for F minus, Cl minus, Br minus, I minus, SCN minus, right? Yes, for NH3, for all of these, they are going to form outer orbital complexes only. After NH3, whatever you have, after NH3, let's say that you have NCS minus, okay? Let's say that you have, what do you have? NO2. So these are going to form inner orbital complexes. They are going to act like a strong field ligand. However, till NH3, all of them are going to act like a weak field ligand. That means they will form outer orbital complexes. Got it? Got it, it seems. Not goatee. Got it? That's what I meant. Okay. Got it? I hope that this is clear. Now guys, we are quickly going to move towards the P block element, and all of these tables that you are going to see here, they are exactly from your NCERT. So don't think that ma'am is giving you something absolutely new and ma'am, oh my god, we have never studied this. Nothing like that, okay? Nothing like that. All of this is there in your NCERT. So you just have to go through your NCERT, go through those tables that are very, very, very important, everybody. For inorganic chemistry, I do not know how many times I have told you, but then once again reiterating this fact that NCERT is your Bible. NCERT is that secret. NCERT is that magic that can fetch you better marks in inorganic chemistry, everybody. So just make sure that you study NCERT completely and thoroughly so that you get more marks in inorganic chemistry. All right, everybody. So chalo guys. Now, I cannot do this. I cannot let my eyes not to be seen at all. Anyway, so yeah, let us talk about the trends and exceptions of boron family. Now we know that atomic radii, as you go from top to bottom, it is supposed to increase, right? It is supposed to increase. However, we do see an exception right here, everybody, because we know that it is boron, aluminium, gallium, then indium, and then thallium. That is Bal Gangadhar Indian Tilak. Or you can also remember it as Baguette, right? Baguette. Baguette is that brand that you have, right? So Baguette, that is B-A-G-I-T, Baguette. That can be your mnemonic, right? Anything, however you want to. But what happens is we should be having, it should be like B-A-L-G-A, then iron, and then thallium, right? So it should increase as you go from top to bottom. But we see a slight twist here. What is the twist here? So it goes like this, it increases, but then what happens is aluminium is slightly bigger than gallium, okay? And then what happens is gallium is lesser than obviously indium, and indium and thallium are almost equivalent. Do you know why? You all know, everybody knows. Yes, very good. Yes, what is it? The correct answer is that the introduction of d orbital happens just before gallium. Yes, so when this introduction of the whole d orbital, the d block was introduced just before gallium. So what happens to gallium is that gallium is like, no, Baba, no, I cannot take it. I'm feeling very shy. So gallium is like, no, I'll stay in a corner. And the size reduces because everybody knows that d orbitals have the worst case of shielding effect. Actually, not the worst case of scenario. I mean, they have a very bad shielding effect, definitely, no doubt about it. The worst case scenario is with F block orbitals. Yes, the F orbitals, they are the worst case scenario of shielding effect. D orbitals are a little better than F, but even then, like, does not really matter. They are still bad, right? So because of the introduction of the d orbital, you see there is a sudden switch in the gallium and aluminium. Again, similarly, indium and thallium, no doubt that we can see here that indium is slightly smaller than thallium. Yes, but like I said, slightly smaller than thallium. Baba, you have to understand this way. So you are increasing the number of shells by plenty. From indium to thallium, you have increased one shell completely. It's supposed to be a lot bigger, but it's not so. Why? Because just before thallium, now what happened? All the F block elements are in the picture. The lanthanum and the actinum, the lanthanoids and the actinoids, they are in the picture. And like I just told you that the F orbitals are the worst case scenario of shielding effect ever that you can find. Hence, thallium, the size, the increment in the size from indium to thallium is not so much. Okay. Now, in case of ionization energy, once again, ionization energy, the general trend in ionization energy is that as you go down the group, the ionization energy decreases. But once again, we do not get to see that here. We see that boron has extensively high ionization energy, which is obvious because anomalous property. Boron is of very small size. The nucleus are very close to each other. I mean, the nucleus is very close to the electrons. It can pull the electrons in its, field of force and everything. But after that, you see, it is directly thallium, then gallium, then aluminium, then indium. What is the reason? What is the reason here? For thallium and gallium, what is the reason, bachos? For thallium and gallium, why did they come in between? That's because f orbital and d orbitals were introduced just before these elements. Hence, because of poor shielding effect, the ionization energy increased for them. Understanding, right? Poor shielding effect, that means that now the electron and the electrons are visible to the nucleus. The nucleus is able to see that, these electrons are roaming around, so I have to catch them and bring them closer. So the nucleus did that. And when the nucleus did that, now your ionization energy increases because you have to give in more energy to be able to, take it away from the nucleus. Understanding? Yes, great. Now moving on, electronegativity. Same with electronegativity. What is electronegativity? In case of electronegativity, we see that a shared pair of electron is pulled by one of the atom. And yes, you see that because whenever there is the f orbitals or the d orbitals are in picture, it will happen that the electronegativity will increase because of poor shielding effect. Now the size of the atom is smaller. So what will happen is that the nucleus will also be able to pull the shared pair of electron more towards the atom. That is why electronegativity also decreases. In case of oxidation state, my dear students, we see that the general oxidation state of this whole group is +1 and +3. However, as you go down the group, the higher oxidation state, stability of the higher oxidation state decreases. Why? Inert pair effect. What is inert pair effect? Inert means that somebody tries to be, very sadhu. They don't want to mingle with anyone, right? Yes, what is pair? Pair means two electrons, right? Effect. Who is going to show this? Who has two electrons? S orbitals. S orbitals have two electrons, so that means that the S orbitals, they are going to act like inert. They are going to act very noble. They are not going to mingle with anybody, and hence you see that the stability of the +1 oxidation state increases as you go down the group. Okay. Alright, the metallic character increases down the group. Yes, we know this. Melting point, it decreases up to gallium and then it increases. Okay, it decreases up to gallium. Boron has very high hardness, bachos. Boron has such a great crystal lattice that it is almost, the hardness is comparable with diamond, everybody. Okay. Yes, so boron has very good melting point, but it decreases up to gallium. That means aluminium has lesser melting point than boron. Then it is gallium. Gallium is so easy. It is very easy to melt gallium. You can just keep it in your hand and it will melt, right? Yes. So it decreases up to gallium and then increases, and then for boiling point you see that it decreases down the group. There is no exceptions here, and density increases down the group. Obviously, the more you go down, you will see that you find more heavier elements, isn't it? You find more heavier elements, hence obviously the density increases. Now let us talk about the reactivity with air. Okay, so this family, the whole family of boron, that is baguette, that is boron, aluminium, gallium, indium, thallium, they do react with air to form oxide. But aluminium is slightly unreactive with air because you get a they form a protective oxide layer which does not allow the the layers which are below to get oxidized. Yes, but aluminium is not that very reactive with air, by the way. Yes, Now, crystalline boron. Boron is also very unreactive because like I just told you that boron has a very, very, very strong crystal lattice which is called as icosahedron. It has 20 faces and 12 edges. I have told you this, right? And the hardness of the lattice can be compared with diamond. But if you take amorphous boron, that means if you take the powdered form, it will react. The powdered form will react. The crystalline form does not react. Aluminium forms an oxide layer which does not react, which does not allow the metal to react further. Cool? Yes, reactivity with acids and alkalis. So boron does not react. Once again, boron does not react. Anomalous properties, yeah. The first element always is a little weird. So anomalous property, boron does not react. Okay. Aluminium reacts with both acids as well as alkalis to liberate, because we know aluminium oxide is amphoteric in nature. Don't we know this? We do know this. So it liberates hydrogen gas, and aluminium is slightly passive with concentrated nitric acid. You know why? Because there is a passive layer of oxide formation once again. Because it forms an oxide layer, it cannot help but not to react. It does not want to react anymore. It has formed a passive layer already. Now we're going to talk about reactivity with halogen. This whole group, it does react with halogen, but what are they going to form? Because their oxidation state, the general common oxidation state of this group is +3. That means they form trihalides. What do they form? They form trihalides. But are they all going to do that? No. You do not get a triiodide of thallium, by the way. Okay, you do not get a triiodide of thallium, and that is an exception. Please make sure that do not write it as same as. Don't write it exactly, don't follow the general trend and write anything and everything, because if from inorganic they will mostly ask you about these mysteries or the twist. But remember, what did I tell you? I told you one day, I told you the other day when I was teaching you, I told you that these are not exceptions. These are actually basically just nature following its rules. We think of it as an exception because it is just not behaving the right way, but it is behaving. In science, they will always follow laws. So just use a little bit of common sense and you will be able to write it, okay? Yes. Next, what are the nature of this trioxide? So you will see that boron, because it is a non-metal, it will form an acidic oxide. Aluminium and gallium forms amphoteric oxides, and indium and thallium, because they are metals and because they are in +1, +2 or +3 oxidation state, they are going to be basic in nature. Please remember this, everybody. +1, +2, +3 oxidation state of metals are always basic in nature. But as and when you increase the oxidation state, the acidic character in them also increases, especially for oxides. Okay? Yes, the +4 and +5, they are amphoteric in nature. +6, +7 are always acidic in nature. Cool? Okay, guys. Now we're going to go to the carbon family. In case of carbon family, we see that as and how the atomic radii is supposed to increase, it does. So you will have chemistry, sir gives snappy problems. You will have carbon, silicon, germanium, that is tin, and then lead. Yes, it is followed. Here there is no exception. The atomic radii is fine. Ionization energy, however, changes slightly. Why so? Because you get to see that in case of lead, right, just before lead, once again you have the f orbital. And because of that, you see a slight change in the ionization energy. And let me also tell you that in this group, most of the exceptions are showed by carbon and it is showed by lead. You will only find exceptions in case of carbon and lead. Carbon, because of its anomalous properties, that means because it is the smallest size of atom in the whole group, so it is going to behave a little weirdly. And lead also shows a lot of exceptions, all because of the poor shielding effect of f orbitals, which are just below these elements, right? Now, when we come to electronegativity, my dear students, in case of electronegativity, once again, we see that first it is carbon, then it is lead. And after that, for silicon, germanium and tin, it remains almost same, almost similar. Once again, do you see how lead has showed an exception? Yes, absolutely, right? Now we're going to talk about the oxidation state. The general oxidation state for this group or this family is +2 and +4, everybody. However, as you go down the group, what will happen? The stability of the higher oxidation state, it will decrease and you will be able to see +2 oxidation state more. Why so? Inert pair effect. Please do not forget that the reason here is only inert pair effect for oxidation state. Okay. And metallic character, obviously as it is, it increases down the group. Now, the melting point, it decreases up to tin, okay? The melting point, if you go down from carbon, then silicon, then germanium, then tin, it decreases, decreases, decreases. And then it increases suddenly. Once again, why? Lead. Before lead, what do you have? The f orbitals have been introduced. Post-shielding effect of f orbitals. It has increased, okay? The boiling point, it decreases down the group. Carbon has exceptionally high boiling point, as you all know, diamond, right? Density, my dear students, density, if you take carbon graphite, okay, if you take carbon graphite, then yes, it will be like this, it will be like this, all right? Then this is what is followed here, this is what is followed here. But by chance, if you take carbon diamond, then what will happen is silicon will come first, then diamond, then germanium, then Sn, and then finally you will have lead, all right? Yes, everybody? So this is for density. Now, we will go to property, reactivity with air. Yes. It does react with air to form monoxide and dioxide, which we all know. Carbon can form monoxides as well as dioxide. Yes, it reacts with water as well. But here, the only exception here regarding tin is that tin reacts with steam, whereas the rest, all of them, they do not react with water in any form. Carbon does not react with water. Silicon does not, germanium does not, only tin can react with steam, okay? Only tin can react with steam, none of the other elements can. If they react with halogens, they form dihalides and tetrahalides, obviously, because their general oxidation state is +2 and +4, correct? Okay. Now, in case of carbon and silicon, we get to see catenation to quite a large extent, right? To quite a large extent, we can see catenation. However, lead cannot show you any catenation, my dear students. You do get to see a slight bit of catenation in case of tin as well, which is almost equivalent to germanium, but not so much as carbon. Carbon can show you the most amount of catenation, then silicon, then germanium and tin on almost on the same level. Lead cannot show you catenation at all. Now here you see that the bond enthalpy of C and C, it is very high. Look at this. It is 348 kilojoule per mole. That means it is harder, it is tougher to break the carbon-carbon bond. It is slightly easier to break the silicon-silicon bond. It's even more easier to break the germanium-germanium bond, and to break the tin bond, it is almost similar to germanium, yes, and the value, my dear students, is the value, everybody, is 240 here, okay? For silicon, for SN, that means for tin and tin, the value here is 240 kilojoule per mole. And here what is written is that due to property of catenation and the p-pi bonding formation, carbon is also able to show allotropic forms. What are the allotropic forms? Diamond, graphite, yes. From diamond and graphite, they might ask you a question, and the exception regarding diamond and graphite in case of density, I have already told you. Sure. Now guys, let's understand the reactivity towards halogen. So when the central metal atom in these halides, okay, if and only if they have sp3 hybridization, then the molecule is going to be in tetrahedral shape. For example, you must have seen for CH4, right? You must have seen tetrahedral shape CH4. But you know what? This does not happen in case of SnF4 and PbF4. These are ionic in nature. These are ionic in nature. Otherwise, we all know the carbon, the capacity of carbon to form covalent bonds, isn't it? Exactly. Also, in case of tetrahalides, you do not see that PbI4 is born. You know, PbI4 is not formed at all. It does not exist. You will never find this compound. Why? Because the PbI initial bond formation, during the reaction, it cannot even raise enough energy. It cannot even get that much energy so that it can, it can, what do you call it? Energy to impair 6s2 electrons and excite them. It cannot. Just cannot. It cannot excite them to a higher orbital, and then then only it will have 4 unpaired electron around the around the central atom, isn't it? But that does not happen in case of PbI4. There is just not enough energy for PbI4 formation. So you see that this compound does not exist at all. Okay. Alright, I hope this much is clear. Now, my dear students, we go to the nictogens. That means your group 15, which is your nitrogen family, everybody. In nitrogen family, you see that the electronic configuration is NS2NP3. That means that they can show variable oxidation state. By the way, let me tell you. And here, how do we learn it? We learn it as, okay, this is in Hindi, guys. I do not know if you have anything in English. If you have it, then please write it down in the comment section because I could not find anything for English. However, this in Hindi is Nai Parosan. Nai Parosan Aishwarya se bhi beautiful. That means new neighbor is new neighbor is more beautiful than Aishwarya. That's an English translation, but I learned it in Hindi. I mean, sorry, I was a Kendriya Vidyalaya student and I studied all over India, so I learned it in Hindi, and this is the only mnemonic I know. Couldn't think of anything in English. If you know anything, then please write it down in the comment section. It will be of great help for the next year students. I will definitely use it, okay? If it is interesting, by the way, provided, yeah. Anyway, so we see here that now these guys, do you see here NP3, my dear students? NP3 means that the p orbitals are half filled. And that is why in this family, the nitrogen family, we get to see extra form of stability. Do you know why this extra form of stability arise by the way? This extra stability, it arises because when you have this half filled orbitals, right? Do you know what happens? Okay, let's try and understand it this way. So let's say that I take 3 pens here, okay? I take 3 pens here. Consider them to be electrons. Consider them to be electrons. So let's say this is one orbital, this is one orbital, and let's say that this is another subshell, right? So these are my, let's say that this is my px, this is my py, this is my pz, right? Like this you have. Now, because all of them have the same energy, they are equivalent in their energy, don't you think that this one can come up from here and it can exchange its position? It can exchange its position, right? Like this. Can it not? It can exchange its position. And will you be able to understand that what happened? The electron just exchange its position. What happened? Nothing happened. That's it. They just exchange. Now, while, sorry, while they are exchanging their position, there is some amount of energy that is released. That is called as exchange energy. In this case, in the case of this half filled and the fully filled, the maximum amount of exchanges happen and the exchange energy is so high that you get to see a lot of stability here. Apart from that, you also see that the electrons are filled up in the orbitals in a very symmetrical way. So one, from the symmetry, and the second point is because of the exchange energy, you get to see such a great stability in case of half-filled and fully filled atomic orbitals, okay? Now, what are the properties? The properties that we're going to talk about, first of all, is atomic and ionic radii. In this case, we see that, yes, as they go down the group, the size increases, right? What is the reason? Because obviously, you are increasing the number of shells, so the size increases, right? In case of ionization enthalpy, yes, we do see that it decreases down the group. Why so? The size increases, and we all know that size is directly proportional to, sorry, one second, that's not how you write it. You write it as ionization enthalpy is proportional to 1 divided by size. That means if you increase the size, ionization enthalpy decreases. If you decrease the size, ionization enthalpy increases, okay? Now, talking about electronegativity, we do see that it decreases down the group, okay? Why? Once again, because there is an increase in the atomic size. If there is an increase in the atomic size, the nucleus will not be able to pull the shared pair of electrons towards it. Hence, electronegativity decreases, okay? Alright, everybody. Now, guys, let us have a look at it one by one. So, in case of atomic number, we all know that nitrogen has 7 electrons. Yes, nitrogen has 7 atomic number. Phosphorus has 15. Yes, then you have AS. Okay, it should be AS. It should be AS. That is arsenic. Arsenic has 33. SB, that is antimony. Antimony has 51. And then you have BI, which is 83. Bismuth. Bismuth is 83, right? Okay, now here you see that the atomic mass is increasing as it is. Okay, the atomic mass is 14 for nitrogen, then it is 30, then it is 74, then it is 125, then it is 200. No exceptions right here. Electronic configuration for all of them is 2s to 2p3, 3s to 3p3, 4s to 4p3, 5s to 5p3, and 6s to 6p3, right? Ionization enthalpy, we get to see that yes, it is decreasing as and when we are moving down the group. No exceptions there as well, right? Now, what do we see? Okay, now in case of ionization enthalpy, you have 1, 2, and 3. 3 ionization enthalpies are given. And no, we do not see any exceptions here. The ionization enthalpies are absolutely fine. Electronegativity also. Now, electronegativity, do you see from 70 to 110? That's a good jump, isn't it? Yes, that's a good jump. Why so? Because once again, my dear students, the nitrogen is the, sorry, I was about to fall. The nitrogen is the first element in the group, and it shows anomalous properties, right? That is why you will see that the electronegativity value is lesser in case of nitrogen. That means that it will be able to pull the shared pair of electron towards it. Okay. Covalent radius also we get to see that it is decreasing. Yes. Ionic radius for nitrogen is very, very, very small. Okay. Ionic radius for nitrogen in picometer is very small. It is only 63, my dear students. Okay. Yes, it is only 63. Okay. Melting point is also fine. Melting point is as it is. It is as and when you are going down the group, you see that the melting point is increasing. Okay. Boiling point is also, there are no exceptions as such. In this group, basically, we do not have much exceptions. Okay. We do not have much exceptions, and we see that everything is pretty much same. Okay. Alright guys, now when we talk about the physical properties, we see that all the elements in this group, okay, they are polyatomic, like dinitrogen, phosphorus is in P4, right? So you get to see this. Dinitrogen is a diatomic gas, while all the others are solids, okay? The boiling points, they increase from top to bottom, we see that. Melting point, it increases up to arsenic, and then it decreases up to bismuth. Did I not see that? I must not have seen that, yes. It increases, and then 1860 to 1837. Yes, it does decrease. Okay, it does decrease. Why so? Once again, guys, before bismuth, there will be f orbital. Poor shielding effect of f orbital is the reason. Okay. Then, due to this decrease in ionization enthalpy, there is an increase in atomic size. So, metallic character, it increases down the group, and except nitrogen, all the other elements in this group, they show allotropes. Like for phosphorus, you have white phosphorus, yes, that is the rhombic and the monoclinic, right, exactly. So, you have all those things. You have white phosphorus, you have black phosphorus, isn't it? So we've read about it, but now it's not included in your syllabus anymore, so you don't really have to study. Forget about it. Then, what is the reactivity towards hydrogen? So we see that once these elements, they react with hydrogen, they form hydrides. Okay, they form hydrides. So you form like NH3, PH3, ASH3, SBH3, BiH3. Yes, you get these. Now let us talk about the thermal stability of these hydrides. The thermal stability, we see that NH3 has the highest thermal stability, then it is PH3, then it is ASH3, then it is SBH3, and then it is BiH3. Now the increase in size of the element, which results in weaker bonds, is the reason why the thermal stability of NH3 is so high. Okay, yes, and why BiH3 has such a low thermal stability, that's the reason. Cool. Now for reducing characteristics, my dear students, we see that the thermal stability decreases, right? Thermal stability decreases. If thermal stability decreases, that means you will be able to break the bonds easily. If you are able to break the bonds easily, that means that they can have good reducing characteristics, okay? So we see that BiH3 has the best reducing character, whereas NH3 has the least. Now, when we talk about boiling point, we see that because there is an increase in the size, and NH3 has an exceptional hydrogen bonding. Because of small size of nitrogen and small size of hydrogen, we get to see that in NH3 hydrogen bonding is there, which is why the boiling point, my dear student, please make a note of it. This is exceptional here. So you see that PH3 has the lowest boiling point, then it is ASH3, then it is NH3, then SBH3, and then finally you have BiH3. Okay. Then we go to basic character. In basic character, once again we see that NH3 has the highest basic character, then PH3, then ASH3, then SBH3, and then BiH3. Why so? Increase in the size of the central atom and thus reduction in its tendency to give lone pair. Because this now the size has increased, yes, so it does not want to get rid of its lone pair. Okay, it does not want to give away its lone pair. So you get to see that what happens is the basic character decreases as you go down the group. Okay. All right. Now, my dear students, we come to the next group, which is your oxygen family. What are the oxygen family called as? Do you know? Oxygen family is called as chalcogen. So, nitrogen family is pnictogen, oxygen family is chalcogen, and the last one is your halogen family. After oxygen, you have the fluorine family, right? So, the fluorine family is called as halogen, as you all know. Now, in case of the oxygen family, what do we see? We see that the atomic number is of course increasing. Obviously, I mean, that should not even be an exception. If that is, then I think it will be crazy, right? Atomic mass obviously increases. Yes, electronic configuration, as we all know, 2s to 2p3, 3s to 3p3, 4s to 4p3, 5s to 5p3, and 6s to 6p3, right? Yes, we get to see this. Now, covalent radius is also increasing. Absolutely right. Covalent radius is absolutely increasing. But please do pay a little bit of attention in this case. Okay. Yes, from 66, see, the covalent radius jumps to 104 directly for sulfur. Okay. Yes, the ionic radius, that means E2 minus. Two electrons are lost, and then when it forms an ion, you see that 140, then 184, 198, 221, and then 230. So it is increasing, right? Electron gain enthalpy for oxygen is minus 141. All right, ionization enthalpy is obviously decreasing as we move forward or as we move down. Electronegativity value, I am not able to see it here. I'm not able to see it here. Sorry, I think that's not mentioned. I don't have it here. Density is obviously decreasing. Yes, density is density for polonium. say TAPO. Yes, density for polonium is 1.76, and density is density per gram centimeter cube for oxygen is 3.50. Melting point is 1.32 Kelvin. And polonium, you are not melting. Okay, you're not able to melt polonium. Polonium is radioactive, my dear students, so we are not going to melt it. Okay. All right, then boiling point, we see that, okay, for oxygen it is very less, but as and when you move down the group, you see that it is increasing. The boiling point is increasing till tellurium, but after that there is a drop in case of polonium. Okay, the boiling point decreases in case of polonium. All right, everybody. No, I think, sorry guys, sorry. I think electronegativity was this. Electronegativity was 3.50. Extremely sorry. There has been a mistake because they were not in, they were not in the same line. So I think I've made a mistake here. Electronegativity is 3.50. Electronegativity decreases as we move down the group. Density here is 1.32. Density increases as we go down the group. For polonium, the density is not mentioned. Yes, because maybe it is radioactive. Melting point is 55 Kelvin for oxygen, and as we go down the group, we see that the melting point increases till tellurium, but it suddenly drops for polonium. Boiling point, once again, we see that it starts from 90, then 780, 958, 1260. Again, it drops for polonium, all right? It drops for polonium. So now, my dear students, let us have a look at the chemical properties of this oxygen family. The chemical properties of oxygen family, first of all, let's talk about oxidation state. We know that oxygen commonly can show a -2 oxidation state, right? And you know that the stability of the -2 oxidation state decreases down the group? Yes. Why? Because as the size increases, everybody, when the size of the atom increases, do you really think that it will try to accept more electrons? No, it will not. It would not want to accept more electrons. Rather, because the size of the atom has increased now, it would want to give it away. Like, hey, take it, take the electrons and go, right? So yes, the -2 oxidation state the stability of -2 oxidation state, that decreases down the group because of decrease in electronegativity. Now the tendency or stability of +4 oxidation state in comparison to +6 oxidation state is obviously, there is a mismatch. The +6 oxidation stability, +6 oxidation state stability will decrease down the group. Yes, the +4 oxidation state will increase slightly. Yes. Once again, poor shielding effect and inert pair effect. Because of inert pair effect, you will see that the +4 oxidation state will be majorly seen. Okay. Yes. All right, everybody, that's it. So these are the few things, few exceptions that you know. One thing is that, very bad shielding effect of D and F orbitals. Second thing is the inert pair effect. These are the only reasons for exceptions, everybody, nothing else. Now, does this group, do they react with hydrogen? Yes, they do. Okay, they do react with hydrogen, and you see that they form hydrides of the nature H2E, where you have oxygen, sulfur, selenium, tellurium, and polonium for E. You can substitute E with these elements. Now, in case of thermal stability, we see that decreases down the group. Why? So hydrogen, H2O, water has amazing hydrogen bonding, and that is why the thermal stability is highest for water. Okay. Down the group, what happens is the He bond, the hydrogen and the metal bond, right? It becomes longer and longer because the size of the atom is increasing, hence it becomes easier to break the bonds, and that is why the thermal stability decreases. Okay. Now we're going to talk about reducing character. It increases down the group except water, guys, like I said. Yes, like I said. Now down the group, what do we see? We see that the thermal stability decreases. Hence, obviously, what will happen is that the reducing character, it increases down the group only. It does not increase for water. Okay. Next is boiling point. Boiling point, we see that H2O, water, has a very high boiling point. The rest, they follow H2S, H2SE and H2TE. Water has a very, very, very high melting point. Please do remember it. Why? Only because of the van der Waal. Yes, there is an increase in the van der Waal forces. However, in case of water, there is an exception because of hydrogen bonding. And acidic strength, everybody, increases down the group because the bond length increases. The bond strength decreases. That means that the hydrogen, H plus ions, will be easily dissociated. Okay. Yes, the release of the H plus ions will happen very easily. And my dear students, we have reached almost the end, that is the group 17 halogen family, which is the fluorine, chlorine, bromine, iodine, astatine family. We do not talk much about astatine. Astatine is slightly sort of, outside the family because it is radioactive, right? So here again we see that for covalent radii, for fluorine it is 64, ionic radii is 133, ionization enthalpy. Ionization enthalpy, we see that it is constantly decreasing, everybody. Yes, which makes sense. There is no exception here. Electron gain enthalpy for fluorine is slightly lesser than chlorine, my dear student. You know why? Because fluorine is so small that the incoming electron, they face a repulsion from the existing electrons. Okay. Hence, fluorine is, although we say that fluorine is the most electronegative element, fluorine is the most electronegative element. However, in reality, theoretically, yes, it does sound that fluorine is the most electronegative element. However, experimentally, it has been seen that chlorine is actually more electronegative than fluorine. Chlorine has more affinity towards gaining an electron than fluorine because chlorine's size is bigger. It can accept the incoming electrons. Fluorine cannot. Okay. All right, but the rest is as it is. Okay, electronegativity is, yes, it is very, very, very high for fluorine, but electron gain enthalpy is not as high as chlorine. You get the point? Electronegativity is pulling the shared pair of electron. Electron gain enthalpy is gaining an electron from somewhere. So electron gain enthalpy for fluorine is lesser than chlorine. Electronegativity, however, is more than chlorine. Okay. Yes, electronegativity for fluorine is 4, electronegativity for chlorine is 3.2, for bromine it's 3, and for iodine it is 2.7. Now, melting point here is 54.4 for fluorine, and as you go down the group, you see that it is increasing. For boiling point also, you see that it is increasing, right? Yes, everybody. Now, ionization enthalpy, we have spoken about it. Electron gain enthalpy, we have spoken about it. I don't think there is anything else. And finally, my dear students, last but not the least, we are going to talk about the noble gas family. Yes. The noble gas family, everyone, you know that you have helium, neon, argon, krypton, and xenon, radon. That means, how do you remember it? Hina, Nina, Arite, Karina, Xerox, Ranveer. Okay, this is how we remember it. In this case, you see that the general electronic configuration of the whole group is Ns2, Np6. Ideally, they should not be forming any compounds. However, xenon has a very similar electronegativity as oxygen, and it does form certain compounds, right? Yes, but those compounds are no longer there in your syllabus. Okay, so the ionization enthalpy, it obviously decreases down the group because the size is increasing. Because of the stable electronic configuration, they have fully filled electronic configuration, plus they have stable electronic configuration. These gases, they have very high ionization energy, right? You cannot easily take away one electron. The atomic radius increases down the group, and they have no tendency to accept the electron, and therefore they have large positive values of electron gain enthalpy. You get my point, everybody? Great. Okay. Now, my dear students, we are quickly getting into a little bit of D and F block, and in the D block, I am going to tell you about the electronic configuration of those elements which are slightly, sort of exceptions. Yes, they are sort of exception. I will not say that they are like completely exceptions. Yes, but they are slightly exceptions. All right, everybody. So for chromium, what is the chromium electronic configuration? The electronic configuration of chromium, everybody, is 4s1, and it is 3d5. Okay, yeah, otherwise all the elements in the 3D series, that is scandium, titanium, vanadium, manganese, iron, cobalt, nickel, yes, zinc, they all have 3s of 3d5 or 3d whatever, 4s2. They have 4s2, 3d1, 4s2, 3d2, 4s2, 3d3, 4s2, 3d4, 4s2, 3d5 does not exist. 4s2, 3d, yeah, 4s2, 3d5 is for manganese. You do not have 4s2, 3d4, I think. No, you do not have 4s2, 3d4. You have 4s1, 3d5, which is your chromium. Okay. Now moving on to copper, you will have, for copper, you will have, my dear students, 4s1, 3d10. Okay. All right. Yes. Then what do we have? After that, we have niobium. Niobium has last outermost electronic configuration as what was niobium? Niobium has, what is the atomic number, guys? Niobium atomic number, and anybody, can somebody tell me what is niobium's atomic number? Can somebody tell me? 41, right? It should be 41, I guess. So 41, that means that it is 5s1 and 4d4. 5s1, 4d4. Okay. Then we have molybdenum. So molybdenum is just after niobium. So it will be molybdenum. Molybdenum is 5s1, 4d5, right? Yes. Okay. Then you have Tc. Tc is technetium. Technetium will have what? 5s2, 4d5. Do you see what is happening here? Do you see what is happening here? Great. Okay. Then you have ruthenium. Ruthenium is 5s1, 4d7, my dear students. Rhenium has 5s1, 4d8. Okay. Then you have palladium. Okay, palladium is important, guys. Palladium is important. Everybody, please pay attention. Palladium has only 4d10. Okay. Then you have Ag. Ag is silver. Silver is 47, and silver has electronic configuration. What was silver's electronic configuration? 5s1, 4d10. Everybody, yes. For lanthanum, lanthanum is 6s2. Lanthanum is 6s2, 5d1. Then what do you have? Platinum. Platinum is also exceptional. Platinum will have how much? What was platinum's? Wow, I have forgotten. For platinum, it was 4f also gets introduced here, no? So 6s1, 4f, 14, 5d9. Okay. Then you have gold. What is the electronic configuration of gold? Ask your mom. Oh my god, all of your moms are going to be very angry with me. No, don't ask. Okay, let this be our joke. Anyway, so guys, gold electronic configuration is atomic number 79, atomic number is 71, and here you have 6s1, 4f14, and 5d10. Okay, this is for gold. Then you have actinium. Actinium is 89 atomic number, and here you have 7s2, 6d1, and finally you have Rg. Rg is 7s1, 5f14, and 6d10, my dear students. Okay, so this is what you have for the electronic configurations that are, the electronic configuration that are exceptional. Yes. Now guys, let us have a look at the melting point and the boiling point graph. So we see that the melting point and the boiling point graph, it does increase as you increase the number of unpaired electron. And we know that as you increase the number of unpaired electron, it increases, but it also does, it also does decrease after a while. So we get to see that tungsten, then molybdenum and chromium, they have the highest melting and the boiling point. However, there is a slight dip in manganese, technetium and rhenium. Why so? In any row, the melting point of these metals, they rise to a maximum of D5. Whenever you see that there is D5, you all know that chromium has D5, isn't it? 4s1, 3D5. That means that chromium can actually get rid of 6 electrons. Literally 6 electrons, my dear students. And these 6 electrons, because they are all unpaired, they can be given up in the kernel of the metal, the sea of metal electrons that they have, the sea of metal atoms that is there. So they can donate it in the kernel, and that's why they have a stronger bond formation, which is why you get to see a very high melting and boiling point. Okay, all right. However, for manganese and technetium, it falls regularly as the atomic number increases. Okay, this is what you get to see. All right, this is what you get to see. Cool, everybody. This is clear. What you have to remember is tungsten has the highest, then molybdenum, and then chromium. And you also see that as and when you go from 3D to 4D and then you 5D, you go to 5D, the 5D series has a higher melting point. Now do you understand why tungsten is used as the filament of the bulb? Do you actually see how high the melting point is? So tungsten has one of the highest melting point in the whole metal world. Okay, yeah, all right guys. Enthalpy of atomization. What do you understand by enthalpy of atomization? Enthalpy of atomization is, it means that how much energy do we have to give to convert a molecule or to convert one metal into an atom? We are trying to convert it into just one single atom, and that's called as enthalpy of atomization. Once again, we see that the enthalpy of atomization also increases as you go from 3D to 5D, 3D to 4D to 5D. That means chromium, then molybdenum, and then tungsten. Tungsten once again has the very high enthalpy of atomization, and from here we can also explain the melting and boiling point. Based on enthalpy of atomization, we can explain the melting point and boiling point as well. All right. Now when we come to atomic radius, my dear students, if you remember, atomic radius depends on two factors. One is the one is the nuclear charge, and the other one is what? The other one is screening effect. Yes. So if the nuclear charge increases, then the atomic radii decreases. If the screening effect increases, atomic radii increases. So we see that from scandium, okay, from scandium, if you go, everybody, from scandium, if you come down till manganese or if you come down till chromium, you see that the atomic radii is decreasing. Decreasing as in, what did I say? Nuclear charge. Nuclear charge is predominant here. Hence, you see that the atomic radii is decreasing. But then from manganese to cobalt, you see, or from manganese to nickel, you see that there is not much difference, right? There is not much difference in the melting point. There is not much difference in the atomic radii. Why so? Because at this place, the nuclear charge and the screening effect both are compensating each other well. Okay, so they remain same. But then again, you see that from copper to zinc, it increases. Why so? Screening effect has increased. Okay, and similarly you get to see that from yttrium to cadmium, that is the similar case. From lanthanum to mercury, it is almost the similar case. Okay, same thing, everybody, just remember this. Okay, you also see that the atomic radii decreases as you go from 3D to 4D to 5D series. Okay, all right guys, now we're going to talk about the trends in stability of higher oxidation state. Okay, so we see here everyone is that till till cobalt, okay, till cobalt, it forms compounds with F. Okay, it forms compounds with F, and it forms compounds with basically the halogens. It does. But after that, you do not get to see any other compounds which is in the +3 oxidation state, in which the metal is in the +3 oxidation state and it is forming a compound with the halogen. You get to see only till cobalt. In fact, for +4 oxidation state, you only get to see till manganese. After that, for iron, cobalt, nickel, copper, zinc, you do not get to see +4 oxidation state with halogen, everybody. And when it comes to, when it comes to halides, when it comes to forming compounds with halides, we see that only chromium can show the highest oxidation state, which is +6, not even manganese, okay? Manganese can show highest oxidation state only when it is forming a compound with oxygen, not with halide. When it forms a compound with oxygen, yes, manganese can show +7 oxidation state, and like I told you that +1, +2 and +3 oxidation state, these are completely basic, okay, these are completely basic. +4 right here is amphoteric, okay, this is your amphoteric, everybody, and +5 to +6, these are your acidic oxides, okay, these are your acidic oxides, my dear students. You have to remember it. Please do remember it. +1, +2, +3 are acidic, are basic in nature. +4 is amphoteric, and +5, +6, +7, they are acidic in nature. Cool. All right, everybody. Great. Okay. Now we see that the oxidation number 2 and 4, they do occur particularly when they lead to a noble gas configuration, especially in case of D block elements. You will be asked questions regarding cerium, you will be asked questions regarding europium and terbium, and you will be asked questions regarding ytterbium. These are the four elements that mandatory they will ask you questions regarding, okay? If at all they ask you a question from F block, otherwise most of the questions will be from D block and coordination compound. If it is from F block, then guaranteed it will be cerium, europium, terbium and ytterbium. So please do remember which one is a good reducing agent, which one is a good oxidizing agent, which one has a tendency to move to +4, which one has a tendency to move to +2. These are the only things that you have to remember. And with this note, my dear students, we have come to the end of the session. This is all your inorganic, because you do not have any other thing. You do not have S block. You do not have metallurgy. You do not have to study environmental. You do not have to study nuclear chemistry. All of that is poof, gone away. Yes, faded away, everybody. So let me tell you, everybody, in Vedantu, we have launched something that is called as Vedantu Daily Practice Problem. So after this class, just below this video, you will get a link. Go to the link and solve the questions. It will be beneficial for you. It will be a good practice for you. Do not forget to join our Telegram channel. In the Telegram channel, you will be getting the notes, and trust me, it is going to be beneficial for you. And with this note, everybody, thank you so much. You guys are the best. Yes, dhanyavadagalu. And have a nice day ahead. Study well. All the very best. Keep studying and stay tuned to this channel, everybody. We are trying to bring you as much content and as much, helpful things, all sort of helpful things. You see, we do not even make memes. You see that we do not do any announcement which will, waste your time. We do not do any sort of those things. So follow us. We are good people. Okay. Tata, bye bye, everybody. Lots of love.